Hi everybody. This video is about defining your PMDC motor choice. When you start designing an application with a motor inside, you have to take care of a lot of requirements. So you have load related requirements. Probably you have a requirement on the starting torque, the acceleration torque, and of course torque and speed in your operating point. Then you have probably requirements on the maximum axial load force or the radial load force. And of course, you have a constraint on the maximum dissipation because the motor may not get too hot. Other technical requirement could involve the maximum starting current because that's a requirement to the power supply, your amplifier or driver. You have a requirement to the power supply voltage, and there are requirements to the dimensions. Then you have a requirement to the ambient temperature in which you want to use the motor, and probably there are requirements on dust and waterproof. And of course, there is a lifetime requirement. What are the number of turning hours? And last but not least, there could be requirements on EMC. Then there are non-technical requirements like requirements on costs, requirements on availability, short-term availability, but also long-term availability, and on serviceability. Well, in this video, we discuss the technical requirements and the impact on the motor choice. So well, let's start off with a small recap of a PMDC motor. Let's start off with a torque speed characteristic. We're not going to do it in detail because then I would refer you to a video in this channel which discusses the PMDC motor torque speed characteristic in more detail. So how did it look like, the torque speed characteristic of the PMDC motor? Well, it was this plot, with on the horizontal axis the motor speed over here and the motor torque on the vertical axis. And you see that the torque speed characteristic is a straight line with an intersection point on the horizontal axis over here, which is the no load speed. And we can define the no load radial speed as the motor voltage U over the motor constant K. So it's U over K. On the vertical axis, we have an intersection point over here, which is a stall torque. It's also the maximum torque the motor can deliver, and that torque is equal to K times U over R, so the motor constant times the motor voltage divided by the motor resistance. And we have seen that when we increase the motor voltage, this line, this characteristic, will increase parallel to the original one, so it will increase to this side. And when it decreases, it goes parallel lower than the original one. Okay, it's based on two equations. The static motor voltage equation, U is K times omega plus R times I. So the back EMF, K times omega plus R times I. And we have the relationship between motor current and motor torque, I equals T over K. So we can substitute the I over here, and then we have the relationship between the motor torque and the motor speed over here. Let's start off with the maximum starting torque and acceleration torque for a motor. Well, this is my motor speed torque characteristic, and in this plot we plot the load curve. So this is my load curve with a maximum static torque over here and a dynamic torque, which we see over here, consisting of constant friction and a damping of the motor. So we see over here that this is my maximum load torque, and the subtraction of my maximum motor torque and my maximum load torque is my acceleration torque. And based on that acceleration torque, we can define the maximum acceleration, which is the acceleration torque divided by the total inertia reduced to the motor shaft. So it's not only the motor inertia, but also the reduced load inertia, which is on the motor shaft. And then we can calculate, as I said, the maximum acceleration. But in a situation where we have an imposed acceleration, like in control circuits, speed control or position control, then we have to do it the other way around. We have an imposed acceleration, so an imposed acceleration torque. We have to add that to the maximum load torque, and then we get a requirement to the maximum motor torque over here. So the maximum motor torque is equal in that situation to my maximum load torque plus my maximum acceleration torque. And for the non-controlled motor, we have seen that the maximum acceleration is an outcome. Well, that is about the starting torque. Now let's look where we can find the relevant data in a datasheet. And I have a datasheet over here from the German supplier Bühler. This is the type number of that motor and it's ending with 235, so we have to look at this column. So which of the data is relevant for this calculation? Now, first of all, it's the motor voltage, 12 volt in this case. And then we see over here that the maximum stall torque, so my maximum motor torque, when I apply 12 volt to the motor, is 64 Newton centimeters, so 0.64 Newton meters. We have also a specification on the maximum current, the stall current. I come to that later. And for calculating the maximum acceleration, we need the rotor inertia over here, 180 grams centimeter squared. So check number one should be, is my stall torque big enough? Because that is what I require from the motor. But we also want to check whether or not my stall current isn't too high, because that is a requirement for my power supply and for my amplifier. Okay, now let's look to the operating point, to the intersection point of my load curve and my motor curve, which is over here. And in that operating point, my motor torque and my load torque are equal to each other. So that's over here. This is my operating point. And when we have a transmission in your system, then the motor torque is equal to the reduced load torque. So at that operating torque, we can calculate what the what the speed will be in my operation point. And of course, the speed in that operation point has to be the omega, the speed which I require, or even higher. It's not a problem when it's higher because then we can reduce the PWM to the motor, so we reduce the motor voltage. So this motor speed characteristic will drop, but it will be parallel to the original one. So then my speed in the operating point, when this is my constant value, will lower until the value that my speed in operating point is the required motor speed. On the other hand, when the speed in the operating point, given this value, given this torque value, is too low, then we can't use the motor. Then you have to switch to another motor. So that is check number two. In the datasheet, these parameters are important: my motor voltage, my motor resistance, and my motor torque constant, my motor constant, also called the torque constant, but because based on that, we can calculate what the speed in the operating point will be. Remember, this is the motor voltage equation and this relationship between the current and the torque, and I can substitute this in this motor equation, and then I can calculate the omega. So why is it important to know the current in my operating point? Because that could also be important. Well, that is a requirement to the amplifier or driver. The amplifier or driver should supply that current. So check whether or not your current required from the motor meets the specification of the amplifier or driver. It's also important because it determines the dissipation of the motor. And the dissipation, we can calculate that when we use a simple thermal model. And in this thermal model, we have a thermal resistance over here, a thermal resistance between the motor winding and the ambient temperature. And thermal resistance is defined as the way a motor can get rid of its heat. When the thermal resistance is high, the motor isn't able to get rid of the heat very easily. So given a power dissipation which flows through the motor and giving the thermal resistance between the winding and the ambient, we can calculate the winding temperature based on the ambient temperature. And we can do that by using Ohm's law in a thermal way. And in that Ohm's kind of thermal law, the voltage becomes a temperature, because in a normal situation when we have an ohmic resistance over here, this is a voltage. So the voltage becomes a temperature in Kelvin, and the current which flows to a normal resistance is power dissipation which flows through the thermal resistance. So the current becomes power and watt, and then my resistance becomes a thermal resistance with the unit Kelvin over watt. So based on that, we can say that the delta temperature, T winding minus T ambient, divided by the dissipation power over here, has to equal the thermal resistance between winding and ambient. So T winding minus T ambient dividing by the dissipation power equals the thermal resistance. So based on this equation, we can calculate the maximum winding temperature, which is equal to the ambient temperature plus the dissipation power times the thermal resistance between winding and ambient. And when you want to have more information about that, please look to the video about the thermal model of a DC motor in this playlist. So when we have that, we can look to the datasheet which parameter is important, and it should be the thermal resistance, and well, it's over here. It's 9.5 Kelvin per watt for this motor. So check number 3 should be if the losses are mainly copper losses, then my dissipation power is I squared times R, and my winding temperature could be calculated on this formula. So it's the ambient plus the dissipation power times the thermal resistance. The maximum winding temperature, the maximum allowed winding temperature, depends on the isolation class of the motor. This is a so-called Class F motor, and for a Class F motor, it applies that the maximum winding temperature is 155 degrees. So it should never increase the value of 155 degrees. But be careful because you have tolerances on the motor parameters, you have tolerances perhaps on your load, but also when when the resistance when the motor is heated, this resistance goes up and the dissipation will become more, so the winding temperature will even increase. So you have to derate this factor. So stay well below the maximum value of 155 degrees. Okay, but what is if the load is not a constant load but is intermittent? Well, let's look to an example of an intermittent load. It's an example from the printing industry where we have a sheet over here which is printed. So the sheet is transported in this direction, so it makes a step, then it stops, then the print is made from the carriage movement, then the carriage stops, then the print, then the paper moves again, then the carriage moves again. So we have this situation in which we print, we step, we print, we step, etc. So from a carriage point of view, the motor is off and on and off and on and off and on and so on. So we can now define the torque duty cycle, which is equal to the on time of the motor divided by the on and off time of the motor. And then we can calculate the dissipation of the motor, which is equal in that case to the torque duty cycle times the average power dissipated in the motor, I squared R, during that on time. And of course, the I can be calculated from the motor torque using this equation, I is T over K. Note that this only applies if the on time is much lower than the thermal time constant. So let's look to the data sheet and we find over here the thermal time constant, which is for this motor 9.5 minutes. So the on time should be at least 10 times lower, and then you may use the torque duty cycle. Okay, what if we use a control system? Well, what is an important aspect in that situation? Well, in a control system, we have a set point, and suppose we have a speed control system and my speed set point is trapezoidal. Then my speed, which I impose as a set point to my control system, so also to the motor, looks like this. We have a part in which the motor accelerates, speed goes up, then we have a part in which the motor speed is constant, and we have a part in which the speed decelerates to zero again. So my motor acceleration will look like this. Constant acceleration, zero acceleration, and a negative acceleration, so it's a deceleration. So at this point in time, both my acceleration is at the maximum, and at this point the acceleration is at the maximum, but also the motor speed is at its maximum value. So what happens then? So let's have a look into this part in time. And I made a picture over here, and during that time I put the omega, the motor speed, on the horizontal axis and the motor torque on the vertical axis. And we see that during this time my motor acceleration is at a constant value. We see that often the load increases when the speed increases. So at this point, both the acceleration torque and the load torque are at the highest value. So this is the point in time where the acceleration torque is at the maximum value. So check number 4, we have to look to the point where the load is at its maximum value, because at that point my voltage which I require still has to be lower than the voltage my power supply can deliver. Look to the motor voltage equation over here. It says that U is equal to K times omega, the back EMF, plus R times I, and I was equal to T over K. So at this point, here it is. So at that point, we see that the torque, so also the current is at the maximum value. But also my back EMF is at its maximum value because the omega over here is at the maximum value. So this point in my torque, in my speed set point, at that point, my required motor voltage is at the maximum value. So this is the check you have to make. Is the voltage you require on that point, is that still lower than the voltage the power supply can deliver? That's check number 4. So summarize the motor checks all together. Check number 1, check whether your stall torque is big enough, and check whether your stall current isn't too high. Check number 2, you have to check whether in the operating point your speed is at least the required speed from which you require for your motor. Check number 3. Check whether the dissipation, so the torque duty cycle times R squared times R, calculate that and check based on that the winding temperature. You can calculate it by this formula, and you have to take into account all the tolerances you have on your load and on the motor parameters, and check the validity. The maximum winding temperature shouldn't increase the maximum allowed temperature, and take into account your derate factor. That's really important. Check number 4, in the control system, your maximum motor voltage at all points in time should be lower than the maximum power supply voltage the power supply can deliver. And check number 5, you should check the maximum axial load or the radial load depending on your mechanism and the lifetime. And then you know whether or not you can use this motor. But what if? What if the relevant info in your data sheet is not available? What can you do then? The first thing you can do is contact the motor supplier and distributor and ask him or her if there is more motor data available. Second, you can determine the missing parameters by experiments. There is a video in this playlist which discusses this topic. And last, and probably least in this case, you have to choose another motor. Well, that's all about this topic. Thank you for watching, and I see you next time.